Hello and welcome wherever you are to this session of the 30th Orkney International Science Festival. We're all familiar with lasers as a part of everyday life, but what's a maser? Well, it turns out to be something older, but now coming back to the fore. And one of the leaders in the field is with us today. He's Professor Neil Alford of Imperial College London. He's the Associate Provost and Professor of Materials Science there. His specialities include microwave materials and functional materials. So good morning, or should I say now it's just good afternoon, Neil, and welcome.
Thank you very much indeed. Thank you. So I guess we're ready for the slides. Great. Okay. Well, first of all, I'm absolutely delighted to be here at the Orkney Science Festival. And that's for a particular reason. Now, I'm going to talk about the amazing maser and how we got there. But the reason I'm particularly excited is on the next slide. And this is my mother. And the reason there's a particular connection with Orkney is because she was in the Wrens and she was stationed in Orkney in 1944, HMS Sparrowhawk in Kirkwall. So it's a particular connection for me, and having been to Orkney, I can understand why my mother liked it so much. Okay, next slide. Now today, I'm going to talk about three things: microwave materials, that's dielectric resonators, and I'll explain what they are. And then I'm going to explain what a Q factor is and why Russian dolls are important. And then we're going to talk about the room temperature maser. Next slide. So let's start with microwave materials, and in particular dielectric resonators. Well, you may not know very much about dielectric resonators, but you use them every single day. A dielectric is an insulator. It's non-conductive, like glass or sapphire or plastic or a ceramic. And a microwave dielectric has the ability to confine microwaves because it has a higher relative dielectric constant than air or free space around us. So this is important. Next slide. So the next thing to understand is what is a resonator and what is the quality factor that I'm going to be talking about quite a lot. A resonator is a device that oscillates at a single frequency, and that's a bit like a tuning fork. The quality factor, or the Q, which we'll talk about quite a bit, is the frequency of that resonance divided by the bandwidth. And what we want is a very high Q, so we want quite a narrow bandwidth for a particular frequency. And so you can see that in B and in C, in the pictures here, we've got a very high Q, and then in C, we've got a rather low Q. Okay, next slide. So microwave dielectrics are like those tuning forks. For example, a quartz resonator in a watch. And as I said, we use them every single second of the day for mobile communications. And the quality factor is the key property that I'm going to be discussing. Next slide. So in a quartz watch, very briefly, what we've got in there is a quartz resonator, and that operates at a particular frequency. And so we are already using dielectric resonators in quartz watches and in many other applications. Next slide. Now, I'm going to talk about the quality factor. This was the key property that I wanted you to think about. And we call, in a dielectric resonator, which would be in your mobile station, base station, or indeed in your mobile phones, you have a Q factor, which the maximum we could probably get there would be a Q of 50,000. It doesn't really matter what the number is, but it's 50,000, and it confines that energy in the dielectric. Next slide. The highest Q that you can get in a dielectric resonator is known as a whispering gallery mode. And here we've got a Q at 10 gigahertz of 130,000. And this is now only limited by the dielectric loss in the material. Next slide, please. So how do we beat this dielectric limit? The thing we saw before, which is on the next slide as well. Here is a whispering gallery. It's actually at St. Paul's Cathedral. And what happens is that you can talk at one side of the cathedral and your friend at the other side can hear what you say, simply because the waves travel around that gallery. And that's why it's called a whispering gallery mode. That's the highest possible Q we can obtain in a dielectric, and that is the dielectric limit. But how do we increase above that limit, above the dielectric Q? Next slide. What we could do, and this is some modeling that we did quite some time ago now, what we could do is to make a particular type of resonator in which there are lots of shells, and that would confine the mode, the particular energy that we want to confine in the air and give us a much, much higher Q. And what we can see is that if we make those shells aperiodic in thickness, in other words, not all the same thickness, then we can increase the Q quite dramatically. It doesn't saturate, it continues to rise. Next slide. But nested spherical resonators are completely impractical. So what about nested cylinders? And this is why it's a little bit like the Russian doll. Next slide. So we did some predictions about what type of Q we could get with an aperiodic resonator, and it came out to a Q around about 650,000. This is huge, absolutely massive. So let's see if we can do it. Next slide. Well, we had one shot at doing this, and we did, I think, about 6 or 7 months of modeling until we were confident enough to actually build the resonator out of sapphire. And inside there, you can see the aperiodic shells of that particular resonator. Next slide. Here's another picture of it. It's a work of art, actually. It's beautiful. So the point here is that the result that we got with this was almost spot on. It was a Q of 600,000. That was the highest Q ever measured at room temperature. So next slide. So what can you do with a Q factor that is quite so high at room temperature? Well, you could make clocks for frequency standards, you could use them in positioning systems, but an idea that we had is if you have a really high Q and you could confine that energy, you might be able to reach the threshold for masing, make a room temperature solid state maser. Next slide. Now, what is a maser? Well, it's a microwave laser. And in fact, it was discovered, the maser itself was discovered by Townes, Gordon and Zeiger at Columbia well before the laser itself. It has very specialized uses. It's atomic clocks, very low noise amplifiers, radio telescopes, and so forth. And as you can see, it's pretty bulky. So, but what is stimulated emission of radiation? Next slide. Now we're going to go through these slides pretty quickly because it just shows the way that these electrons move from the upper state and to the lower state. So next. So stimulated emission, an electron drops to the lower state, it emits an additional photon. Next. So 2 electrons drop down to the lower state, and next. Emission of 2 additional photons, and next. 4 electrons drop to the lower state, and next, and so on, emission of 4 additional photons. Next slide. So why are we interested in masers? Well, mainly because they offer exceptionally low electromagnetic noise. And what is electromagnetic noise? Well, we all experience it. Next slide. So it's a little bit like trying to hear your child across a very crowded playground. It's really difficult. You need to be able to filter out your child's voice. Next slide. We see that in drop calls with radio telephones. Microwave signals can get blurred and messy. Next slide. So what we want is not a low signal to noise ratio, which is on the left of that slide. Now that's noisy. What we need is we need to amplify that signal, the key signal that we're looking for, to get a very high signal to noise ratio. So it's all about signal to noise. Next. So despite that, radio waves, microwaves, brought this image of the Mars rover 140 million miles away from Mars. The radio transmission itself required a maser on Earth to disentangle that signal and to amplify it. So that's where masers really come into their own. In deep space communications, here we see an incredible picture of the Mars rover. Next slide. Now, why don't we see masers everywhere? Well, because solid-state conventional masers need huge magnets and they need cooling. And you can see that there's a lot of hardware in this conventional Ruby maser. Next slide. And they need cooling, and that's rather inconvenient. There's some person up at the top of a ladder trying to replenish the helium in this particular maser. Next slide. And you can see it's very bulky. So here's Charles Townes, who invented the maser in 1953, and here he is with his maser. It's too bulky, it needed cooling, it needed a big magnetic field, and there was absolutely no prospect of mass production. So it was not too surprising that Townes and colleagues started looking at higher frequencies in order to miniaturize the whole system. So next slide. And here, only a few years later, in 1960, Townes and colleagues developed the laser, and the rest is history. We see lasers absolutely everywhere. And the reason is because they were able to be miniaturized, they didn't need cooling, they didn't need a magnetic field, and they were tiny. So next slide. Now, we looked at organic materials to try to make a maser that would work at room temperature. Now, organics are generally very low melting point, generally. They're mainly carbon and hydrogen. We used a molecule called pentascene, which is basically 5 benzene rings. And pentascene is a pretty well-known organic semiconductor. Its melting point, though, is 300 degrees Celsius, and that's far too low for laser illumination. Next slide. But how did we get there? The idea of organic masers was not new. The first attempt was in 1961. Next slide. And then the next attempt was in 2002, when colleagues in Israel looked at trying to make a room temperature maser. And they concluded that it would not work. Next slide. Basically what that says is that it's not going to work. Well, that was a bit of a challenge. And we also thought that this organic might be quite useful for a room temperature maser. Next slide. And so Mark Oxborough and myself and Jonathan Breeze started working on this, and we made a pentascene in a carrier called pertophenyl, and there is the first room temperature maser crystal. Next slide. And here you can see the setup. It's inside a copper cavity. There is the large sapphire resonator, and inside the middle of that is the active medium, which is the pentascene. So next slide. And this was published in Nature. And the advantage of this is that it's just free electrons. So it could be very, very low noise. Next slide. and capable of miniaturization, because of course we don't need a magnet and we don't need to cool it. So what we're concentrating on at the moment is to see if we can miniaturize this quite substantially. Next slide. But there is a problem. So far, we can only use this particular molecule in pulsed mode. In other words, we have to zap it every now and then with the laser in order not to fry the organic. And that is a bit of a problem because we really would like it in continuous wave. So what we then did was to say, well, what about inorganic materials which have far higher melting points and they have pretty good spin dynamics? What about nitrogen vacancy centers in diamond? Okay, next slide, please. But before we do that, why do ruby masers need cooling? Well, quite simply, there's a thing called spin lattice relaxation, and we would want that to be as long as it possibly could be. Unfortunately, in the ruby maser, the spin lattice relaxation is incredibly fast. It's picoseconds. And so we have to cool it down. Next slide, please. So in diamond, there's a nitrogen vacancy. This is a defect in the diamond. And actually, a defect in this case is a good thing. And what's good about it is that these particular defects have very slow spin lattice relaxation. And when I say slow, I mean milliseconds. Well, it sounds fast, but actually it's not. It's pretty slow. It also has very, very good mechanical and thermal properties with a huge thermal conductivity. Next slide. Now, again, it's not surprising, but many years ago, in 1977, actually, it was thought that a maser could be made using a nitrogen vacancy defect in diamond. Next slide. But I think one of the reasons that it was never really made is because the microwave engineering you need in order to make it work means that you have to have very high Q. We're back to the high Q cavity. And so what we were able to do with a bit of understanding about the material science and the microwave engineering was to make a very high Q factor cavity. And we used a sapphire ring, as we had in the very first maser, room temperature maser. And within that sapphire ring, we placed the diamond. Next slide, please. And there's a picture of the diamond on the left. You can see the little red diamond in there. It's a little bit red because of the nitrogen vacancy defects, actually. And surrounding that is the sapphire ring to give it the very high Q. So next slide. And this is a photograph of the spectrum analyzer that we used to take the very first signal of a continuous wave maser emission. And so that's an incredibly exciting thing to see, I have to say. Next slide, please. So we published that in Nature, but one of the very interesting things that we also noticed is what Leslie will have been talking about previously, and that is, could we use some of these quantum oscillations to make, for example, quantum computers or quantum sensing? And here you can see quantum oscillations. They're known as Rabi oscillations, but they're very, very pronounced, and they're taking place at room temperature, which is remarkable. So the potential applications that we see are in very low noise amplifiers, deep space communications, quantum computing, and quantum sensing. Next slide, please. The important metric we can use to compare this with other masers is the noise temperature. And you can see that at an operating temperature of 4 Kelvin, the conventional masers have noise temperatures of a few Kelvin. Now, in our maser, at 293 Kelvin, which is room temperature, both the pentascene maser and the diamond maser look to have extremely low noise temperature. And the advantage of that is that we can operate devices at room temperature and take the advantage of very, very low noise. And in this case, we've defined the noise by a noise temperature. But basically, very, very low noise indeed. Next slide, please. So, to conclude, really, it was fundamental science that led us to the very high room temperature Q. In itself, that is just a scientific curiosity. But it did make us ask, well, what could you do with a Q that high at room temperature? And that led us to believe that we might breach the threshold for masing, and it led to the very first solid state room temperature maser in the organic material pentascene, and then onto the inorganic material diamond. The potential applications are room temperature quantum electrodynamics as a platform, quantum information processing, spin memories, but really the ultimate low noise amplifier with a very high signal to noise. And for example, that means that we could obtain very, very good magnetic resonance images very fast and with better resolution. So next slide, please. So here's the Curiosity rover, and there we have a picture of it without the noise. I mean, on Mars, we not only do we have the resolution to look at the rover, we have resolution now to pick up the individual grains of sand, which is quite extraordinary. Next slide, please. So in the future, I think that we'll see a whole lot of functionality jammed into a very small device. In fact, it's a little bit like Spock's tricorder. Next slide, please. Thank you very much indeed. Thank you.
And thank you, Neil, for a fascinating insight into some exciting possibilities. The questions have been coming in, and just before we go to one, to summarize the difference between the laser and the maser. In both of them, the same fundamental process is going on, but there's different forms, different parts of the radiation spectrum. Would that be right?
That's exactly right. The maser is, the acronym is microwave amplified stimulated emission of radiation, and for the laser it's light, and that's at a much, much higher frequency. So that's exactly it. It's a difference in frequency.
And the difference in the extent of the problems is interesting too, because the amount of problems with the maser as compared to the laser, it's quite interesting that there's such a big difference.
Yeah, what is quite extraordinary is that these scientists who are working in places like Bell Labs and Columbia and so forth, their inventive capacity was absolutely incredible. It really was. I mean, to get from the maser to the laser in only literally 5, 6, 7 years, it's quite extraordinary. And actually, it's quite interesting to note that when the laser was discovered, they really didn't know what it was going to be used for. They had no idea that it would be used in barcode readers and such like. So it's quite interesting that now we have a room temperature maser. We still don't know what it's going to be used for, really. So it's interesting.
And Bill Graham in Forres asks, did you grow the high Q resonator? Did you grow it, or did you machine it from a crystal?
That's a really good question. So we didn't make the sapphire resonator. We grew the amazing medium, the pentascene. We grew that, but for the diamond, our colleagues at Element 6, they made that particular diamond. But the sapphire resonator, which I think Bill is talking about, was made by some colleagues in Germany out of by Trochalski method, if he knows about crystal growth, and then it was machined out of a large boule of sapphire. So sounds unbelievably expensive, and for a university, it was quite expensive actually, but not as expensive as you would imagine, frankly.
Well, that leads on to Richard Oakley's question. He's been noticing some of the substances, indeed, like diamond and ruby, and specifically sapphire. And he asks, is it inevitable that it's going to be expensive materials like that, or could there be options for some less exotic, less expensive ones?
Well, that's a great question. Actually, diamond is a commodity material. It's used, the sorts of diamonds, the synthetic diamonds that we use are used in drill bits for petroleum engineering. And so actually they're pretty cheap. The diamond itself is one of the least expensive bits of the whole device. So it's not the diamond, it's not the sapphire, it's all the rest of the stuff that you have to do to make it. So I don't think that we're going to be limited. They're not gem-like quality, let's put it that way.
Bill Graham also wonders about resonators, building the resonators. Would it be possible, he says, to build them by 3D printing of a directed vapor stream in vacuum?
That's a great question. Actually, the resonators themselves, the sorts of resonators that we've used are sapphire and the like. But you're absolutely right. We could make resonators out of different materials, out of metallic materials, for example, and we could 3D print those. We may get away with resonators which are simply planar. And I think in one of the patents that we filed, one of the resonator geometries is a screen printed planar geometry. But that's a great question to ask, actually.
Martin de Vries has a question about the applications of masers. He says, other than improving images, what other applications could you foresee for them?
Okay, the critical thing, I think, in the first instance will be this business of increasing signal to noise. So there's a particular thing called phase noise, which is also known as jitter in all sorts of electromagnetic applications and radio waves and in microwave communications. If we could reduce that phase noise, if we could reduce that jitter, then we would improve microwave communications, our mobile phones, quite substantially. There are also a number of areas where you would want low noise amplifiers. So low noise amplifiers are, again, everywhere. They're in not only in MRI machines, they're in all sorts of different imaging modalities. So if we could introduce those low noise amplifiers with much lower noise, then I think we would see an improvement in a number of different aspects of communications and imaging.
There's a question about masers and lasers. We hear about the dangers that can happen with lasers, with a concentrated laser beam. Are there any dangers like this that could happen with masers?
Yeah, I think that it's pretty low. The main danger here, I guess, is the laser that we use to amplify. To illuminate the amazing medium, the diamond, for example. But actually, we're reducing the power required to do that quite substantially, so that we would probably, almost certainly, actually be able to use an LED that you see, I mean, like Christmas tree lights, for example. We would use an LED to illuminate the amazing medium. And then the output from the maser itself is tiny. It's very, very small indeed. So I think going forward, I think the illumination of the maser itself will be very, very low intensity, and the output is tiny. So I don't think there will be a problem there.
A question, a listener in Murray asks, do masers improve the speed of information transfer or just the quantity and particularly the resolution?
Yeah, that's a good question. I guess it's the resolution. I guess if we could, it's not the speed, it would be the resolution and the clarity. So if you can increase your signal to noise, the speed is going to be fixed by the microwave resolution. But the But the critical thing is that we would be able to improve the quality. In other words, the signal to noise. That's the critical thing.
And you mentioned two fascinating phrases, quantum computing and quantum sensing. Could we ask about the sensing, first of all? Is that something that, for instance, could be used in satellite surveillance of the studies of the planet?
Yes, I think so. I think in those sorts of applications, quantum sensing is also possible. Gravity sensing, for example, you could look at buried pipelines with good quantum sensors, gravity sensors. So that's certainly a possibility. That's a long way off. I have to say, the quantum computer is not going to be here anytime soon. Let's make that absolutely clear. It'll be a long way away. But there are certain applications, and I do think that sensing is a nearer one using quantum devices, and ultimately, the quantum computer will require a great deal more research. We've got a long way to go on that one, a long way.
The quantum computer is interesting because the scientific journals or the popular magazines have some fascinating stories about progress towards it. And I guess each person making a development wants to highlight the importance, but you're saying that there's quite a way to go.
I think there is, yeah. I mean, there's been amazing progress in the last 10 years. I mean, it's quite remarkable what IBM and folk like that have done. It's fantastic, but it's still a long way off. It really is. So,
and could you just expand a little about how the maser, the way in which the maser could make a difference in quantum computing?
Well, I think what we've seen, which I guess it came as a bit of a surprise for us, are these quantum oscillations, these so-called Rabi oscillations, and they are those are quantum oscillations that are taking place at room temperature. Now, the idea of at the moment, there's no possibility of having a quantum computer that would operate at anything other than millikelvin. They have to be cooled unbelievably. I suspect that may well be the case even with our room temperature Rabi oscillations because of, again, noise. But it does mean that we can look at certain devices that might make use of these quantum oscillations. And what they are at the moment, I don't really know, but I think that we will find that in due course.
One listener asks, on the subject of quantum computing, is it a bit like nuclear fusion? Meaning, of course, not in the process, but in the time when it might come.
Well, actually, nuclear fusion, that's another thing. I think that's also probably, there's huge advances being made in nuclear fusion, and we can see the jet torus actually being, the progress there is really quite remarkable. And I think what we'll see there is maybe modular fusion reactors, which are much, much smaller. So I think that fusion is something certainly that the UK government is interested in looking at, and I wouldn't be surprised if we could get that right. It would make a massive difference to our energy budget.
But quantum computing could be sooner. Do you think sooner than fusion?
I think it's probably the same, actually. It's probably the same.
One general question about material science. We sometimes think it's sometimes possible to look at the picture of the periodic table and think, oh, well, there's 90, 100 elements, and it seems a bit finite. But is it the case that in material science, there seem to be new horizons opening up all the time?
Absolutely. Absolutely. I mean, it's quite remarkable. What we're seeing in material science now is the advent of computational techniques which are helping in our materials discovery. And so my colleagues all around at Imperial, in London, in Liverpool, they're applying computational techniques to search for new materials. And this is becoming ever more sophisticated. So I think the use of computational chemistry, computational techniques in the search for new materials is going to become more and more important, and it will make a difference going forward. It already is, but that is an area of material science which is going to grow quite substantially.
And interesting too that you're moving into organic materials as well. We think traditionally of the inorganics, carbon and silicon and copper, but the organics, do they again open up new horizons?
Yes, they do. There's a lot of interest in organic material, organic semiconductors for solar cells, for example. There's a lot of work going on in that area. So organic semiconductors are a topic of huge scientific interest. My personal interest is actually in inorganic materials, to tell the truth. And I think that there's still a great deal of really interesting science that we can look at in the inorganics. And indeed, in the maser itself, there are other systems that we think may be able to be used as a maser. For example, silicon carbide, another pretty not expensive material, silicon carbide. And we think that there are defects in silicon carbide that we'd be able to use as a maser as well, which is very exciting.
And a general question about the whole process that's going on. Quantum theory is sometimes spoken about as a bit chaotic, with words like possibilities and even weird. But in fact, from what you're saying, what goes on in the process of the laser and the maser is atoms and energy and everything moving in step.
Yes, well, yes, but it is a quantum device, and quantum mechanics is very strange indeed, as we all know. So, and I don't profess to be an expert on quantum mechanics by any means. I'm a grubby engineer making things. That's all it is. But these are quantum devices, and we need our colleagues to be able to explain to us precisely how these things work well.
But it's very much though this idea of coordination. There seems to be definitely in step, in harmonies. Yeah,
I mean, what you've just said is quite important actually, because when you look at how we developed the maser, the people that we had were on the team were geologists, physicists, organic chemists, inorganic chemists, and underlying all of that was a very good electrical engineering basis. So to find things like this, I think you do need interdisciplinarity. And it's quite interesting to postulate that although people had thought about diamond masers back in the 70s, they didn't bring everything together. So they didn't have the interdisciplinary team to be able to put the microwave engineering with the material science, with the physics, and then produce the result. So, you know, and it's at these boundaries of disciplines where the very interesting science begins to emerge. So I think that this interdisciplinarity is absolutely critical.
And it emerged out of something in fundamental science, something practical emerged almost unexpectedly out of something theoretical.
I guess certainly the looking at this aperiodic resonator, where all we were doing was trying to make the highest Q resonator that we possibly could. And we did, and it was utterly useless for anything else. It was because it was too difficult to make. But what a great, it just opened up that possibility of, well, what could you do with this? Maybe we could make a room temperature maser. Well, that could be useful, unlike the aperiodic resonator, which is not useful. So.
And I wonder too about the feeling that must have been there in the room when you were waiting for that spectrum to appear on the screen. Did you have a feeling?
I've got a picture. I have a picture of that actually, which I didn't show, but I've got a great picture of everybody going ballistic. So yeah, I should have showed that.
It would have been the result of many, many long months, many late nights, early mornings, big
It
challenge.
was. It took. It was a really good collaborative effort with our colleagues at UCL. So on the diamond maser itself, that took a lot of work to get right. A lot of microwave engineering, a lot of physics that went into that. And so our colleagues at UCL and ourselves at Imperial worked together on that, and it worked out. They don't always.
I was wondering too, were there any points at which you thought you'd hit a brick wall, or there was something technically that just wasn't going to be possible to solve?
I think we always thought that there was something that we could overcome, and I think that certainly with the diamond maser, when it became apparent that actually what we really needed was we needed the diamond, the right diamond, but we really also needed the microwave engineering, the cavity itself. And actually, it was Jonathan Breeze who did the microwave engineering to understand. He's a physicist, actually, an astrophysicist, but he also worked for Marconi, and he was able to make that particular engineer that particular cavity so that it worked. And I think that if folk had normally people don't have very high Q cavities in their electron spin, electron paramagnetic resonance machines, but if they had, I think they would have seen it many, many years ago.
Martin de Vries has come back to ask, is it possible to make millimeter wave amplifiers, or indeed is that something that already exists?
I don't think I know the answer to that, but I think in the sense that this is a low noise amplifier, I think that anything at millimeter wave that uses low noise amplifiers would be improved by this particular device.
And one more question's come, Bill Graham. Could the energy of a maser be used to move molecules for materials construction?
Wow. I think, well, first of all, the output from the maser itself is very, very weak. So I suspect not. But actually, I don't really know the answer to that question. I'm just not sure about that. So I suspect it might have an effect, but I think it would be pretty small. But it's not a bad question, the answer to which I'm really not too sure.
And a final question for a young person thinking about a career in science, would you recommend materials science?
I absolutely would, and the place to do it is Imperial College. But actually, no, there are a number of very, very good materials departments in the country, and I think materials science is a great discipline. You have to learn lots of different things, and it's really, really interesting. So definitely, materials is a great subject.
Well, you've certainly brought it to life in an exciting way for us today, Neil. Thank you very much indeed. And before leaving, I should mention that we'll be back at 1 o'clock when we're going to be interviewing the writer of a new book about physics. But it's a fascinating background. She's an artist. It's a book about personal loss, but the physics is brilliantly and beautifully written. Well, that's at 1 o'clock. And there's also spaces, I should say, for discussion and conversation over a bite to eat in the PD Kirk lunches. You can book tables on our booking forms. But all that remains me to do is to thank the technical team behind the scenes for making everything run so smoothly and enjoyably, and to our guest, Neil Alford, for an absolutely fascinating insight into the joys of materials science. So from us all, till tomorrow, goodbye now.